We will continue our discussion on quark model. In the last discussion, we discussed how the mesons can be grouped into a group of 8 and one singlet, considering the flavor symmetry, which is basically associated with what is known as SU3 group. We will continue the discussion on the flavor symmetry and the grouping grouping of hadrons under this. So, today we will look at the baryonic resonances or baryonic composite particles like proton, neutron, etc. To recap, we said U quark, D quark and S quark can be considered as a triplet under SU3 flavor. Similarly, U bar, D bar, the S bar, the anti-quark of this UDS quark also form a triplet of SU3. So, in the case of mesons, we needed to take a product combination of the UDS and U bar D bar S bar to form mesonic bound states. But in the case of baryons, what we will take is a group of triplet of the quarks and another triplet of quarks and another triplet of quarks, one quark each from one group to form a baryonic bound states, which consist of 3 quarks. As per the SU3 group, such product can be split into a singlet, a group of 10, a decouplet, 2 groups of 8 octets. As we mentioned in the last class, this is very similar to the spin angular momentum or normal angular momentum algebra, where when we actually take 2 spin half particles and consider them as a combined system, then the combined system will have or can have spins either 0 or 1. Spin 1 case is actually a triplet with 3 different projections, spin 3 projections, and the spin 0 case is a singlet with only 1 spin projection possible in that. So, the spin 1 can be thought of as having 3 members, a triplet. Similarly, if you take other spins, we can combine them as well. So, in a similar fashion, we can actually think about 3 triplets forming 2 octets and a decouplet and a singlet. One of the octets is formed by the proton, the neutron, the sigma, 3 of them, sigma plus, sigma minus and sigma 0, and 2 other spin 2 other isospin half resonances or particles called cascade particles. Okay. One is cascade 0, the other is cascade minus. So, in the I3 S plane, we can put them arrange them in a fashion very similar to what we had done in the case of mesons. This gives us a group of 7. Along with this, the lambda particle, which is again neutral, isospin 0, strangeness -1. So, here strangeness is 0 here, -1 for the middle point particles sigmas and lambda, and -2 for cascade particles. The decouplet group of 10 can also be arranged in a similar fashion in the S I3 plane. There is a resonance delta plus plus, which can be thought of having 3 U quarks inside it, and a delta plus, which is a UUD, which consists of UUD, delta 0 UDD, and delta minus DDD. These 4 form an isospin 3 by 2, I equal to 3 by 2 and I3 equal to plus 3 by 2, I3 equal to plus 1 by 2, I3 equal to minus 1 by 2 for delta 0, I3 equal to minus 3 by 2 for delta minus. All of them are strangeness 0 particle. So, we can put them in I3 S equal to 0 I3 line as follows. So, delta plus plus with I3 3 by 2, delta plus I3 half, delta 0 I3 minus half, and delta minus I3 minus 3 by 2. Then the rest of them actually will form an inverted pyramid, rest of the members of the decouplet. So, when we consider the next isospin group, that consists of another particle with quantum quark combination U S and sigma 0 with U D S and sigma minus with D D S. Notice that these sigmas have exactly the same quark content as the earlier sigma in the octet. Okay. So, we had earlier mentioned what are the quark contents of the sigmas there. So, what is the difference here? The difference is that they are more massive. All the 3 of these sigmas, which are members of this, have a different mass, higher mass compared to the sigmas in the octet. So, this can be thought of as some kind of a excited state, I mean in a vague sense, of the UUS system. So, you have a quarks 3 quark UUS system, say, the ground state of that will give you the sigma plus, which is part of the octet, and the higher excited state, one of the higher excited states will give you sigma star plus or sigma plus star, which is a member of the decouplets. Similarly, sigma 0 and sigma minus. Then it was observed that there are 2 other resonances which otherwise look similar to cascade. quark content can be thought of as USS, strangeness -2, and a cascade minus with quark content DSS, 2 strange quarks, therefore strangeness -2. But their masses are larger compared to the cascades appearing in the octet. So, we will think about them as the excited states of the same quark combination. At the time, these ideas or this such grouping in super multiplets, bigger super multiplets, I said because we already had earlier multiplets according to the isospin grouping that we had discussed. Now, in these octets or the decouplets, what we are doing essentially, if you look at this, is that considering different such I3 groups and put them in a bigger group here. So, for example, the cascades, the delta minus, delta 0, delta plus, delta plus plus, all the deltas belong to a particular isospin group and all the sigmas belong to another isospin group, I is equal to 1. At the time of such development, when these submultiplets were discussed, those the SU3 flavor multiplets were discussed or developed, we had already observed or these resonances, deltas, sigmas, sigma stars, cascades, cascade star, neutrons and protons, of course. But then there was a natural point in this decouplet grouping. There was one missing particle which was not observed at that time. And as per the SU3 grouping, this should have a quark content of 3 strange quarks, so that its strangeness is -3, isospin 0, isospin 3, 0, and this is basically the last member of that decouplet group, and it was named omega minus. It was predicted that a particle with such and such isospin, such and such strangeness should be there or exists. We will come to the mass relations in a minute, and we will see that mass can also be predicted to some accuracy. And indeed, such a particle was discovered later on in a couple of years, in 61, and this was a triumph of such grouping, SU3 flavor grouping, which gave a big boost to the quark model of the hadrons. So far, we had not observed any free quark. So, the question still was whether quark is actually a real particle or just kind of a mathematical entity. So, we had to wait for a little more while to actually establish the quarks inside the hadrons, of course, as physical particles existing inside the quark, and later on, of course, we had discovered the top quark also. So, unambiguously or at the moment we have no doubt in the existence of quarks as particles. So, now although we have been talking about these quarks, let us summarize this properties of the quarks, associated with the or the different properties associated with the quark. Let me call this as the quantum numbers associated with the quarks. Okay, just a summary of this. We have U quark and D quark, charm quark and B quark. Of course, there is also the top quark, although they do not really form the bound states, they are there. And since 3 of them form bound states called baryons, like protons and neutrons, lambda particles, sigma particle and delta particles, we have to associate the baryon quantum number with the quarks. Baryon quantum number of U quark or each of these quarks should be 1 by 3, so that 3 quarks together add the baryon number to 1. So, we will put 1 by 3 as the baryon number, which we denote by the letter B as 1 by 3 for each quark. Then we said there is this strangeness that we had to consider. So, the strangeness quantum number, U quark has no strangeness. I have to put one more quark there, this strangeness quark. Okay, so this is charm, strangeness, top and bottom. Let me put bottom here and then top below this thing. So, strangeness quantum number, for historic reasons, for strange quark was associated with a strangeness equal to -1. This is because the strangeness initially was introduced by looking at particles like K mesons, which used to be produced in strong interactions of proton-proton collisions, for example, but decay weakly. In fact, this was the reason why these particles were given such an additional quantum number, which is called strangeness. So, these particles were given a strangeness +1, and later on in the quark model we saw that the strangeness, the quark content of the K meson, K plus and K 0 are actually S bar, not S inside that. K plus is associated, or the quark content of K plus is U and S bar. Similarly, quark content of K 0 is D and S bar. So, since strangeness was associated, or +1 strangeness was associated to K plus and K 0 historically as they were discovered, and then found that they behave strangely in the sense that they are produced strongly, but decay weakly. So, S bar quark naturally got a +1 as the strangeness, and S quark therefore got a strangeness -1. B and top, bottom and top will not have any of this thing. So, in a same fashion, we actually have charmness. We can also talk about bottomness, since bottom B letter is already taken up by the baryon number. We will put B prime as the bottomness, and you can also talk about topness. So, you can see that C quark will have charmness 1 and B quark, S quark, all other quarks 0 charmness. Similarly, B bottom quark will have a B minus 1 similar to the strangeness quark, and then top quark will have a plus 1 topness. And isospin, this is half and half for the U quarks and 0 for the other quarks. We can also talk about I3 plus half here and minus half here, and of course 0 0 for the rest of it. So, let me write this, although we have said this clearly. B denotes baryon number, C denotes charm quantum number or charmness, S is strangeness quantum number, B prime is bottomness or bottom quantum number, T is topness or top quantum number, I is the isospin. Okay. And now, not all of these are independent quantum numbers. There are some relations which these quantum numbers together satisfy along with the I should mention the quark, the charge of these particles as well, maybe the electric charge, Q is the electric charge of U quark is plus 2 by 3, electric charge of D quark is minus 1 by 3, charm quark plus 2 by 3, bottom quark strange quark minus 1 by 3, bottom quark minus 1 by 3, and top quark plus 2 by 3. As per Gell-Mann and independently Nishijima, there is a relation between these quantum numbers. Q in units of electronic charge E. Okay. That is what we had done in the earlier slide, in fact, is equal to I3 plus baryon number plus strangeness plus charmness plus bottomness plus topness divided by 2. In fact, later on we will associate in fact this whole thing in the bracket above B plus S plus C plus B prime plus T as what is known as hypercharge. Okay. Hypercharge, and denote this by Y. So, the Gell-Mann Nishijima relation becomes Q equal to I3 plus Y by 2. Okay. So, let us see some of the quarks. Okay. The I3 of this quark, Q of this quark as per the relation. So, U quark I3 is plus half, baryon number is 1 by 3. So, Q should be equal to I3 plus Y by 2. Okay. So, baryon number is 1 by 3, therefore, Y is 1 by 3. So, you have Q equal to 1 by 2 plus 1 by 3 by 2, which is 1 by 6, which adds up to 2 by 3, which is the correct charge that we have for the U quark. Okay. And similarly for the D quark, this is equal to minus 1 by 2 I3 plus 1 by 6, same hypercharge, equal to minus 1 by 3. Similarly, for strange quark, I3 is equal to 0. So, therefore, this is equal to 0 plus y is now baryon number 1 by 3 and strangeness minus 1. So, you have 1 by 3. So, there is an overall 1 by 2, 1 by 3 minus 1 should add up to minus 1 by 3. And similarly, for other quarks, you can work this out and then check that all this Gell-Mann Nishijima relation holds good for all the quarks. Now, we can even extend this beyond the quarks to other multiplets like other bound states as well. So, extending to the mesons, extending Gell-Mann Nishijima relation to the mesons. So, what we have is the same relation. Let me write the relation here, Q equal to I3 plus baryon number B plus S plus C plus B prime plus top divided by 2. So, let us take the octet that we had considered, okay, Masonic octet. So, B baryon number equal to 0 for mesons. They are made of strange quarks, U quarks and D quarks, but no charm quarks. So, C is equal to 0, B prime is equal to 0 and T equal to 0. When we consider the mesons including the charm quark number quarks or made of charm quarks, we had to consider the charmness quantum number as well. Similarly, for bottomness, but baryon number is always 0 for the mesons, because baryon number of a quark is 1 by 3 and a anti-quark and an anti-quark is minus 1 by 3. So, they add up to 0. So, let us consider the octet. Okay. So, one member is, so this is basically I3, right, and okay, let me write it here, I3, and consider start with the K plus, I3 is half and strange baryon number is 0, etc. Strangeness is plus 1, therefore, hypercharge is 1 and Q equal to I3 plus Y by 2, Q is equal to half plus 1 by 2 is 1. That is fine. Okay, let me write it as half plus half equal to 1. When we consider K0, hypercharge is the same, S is the same, but I3 is minus 1 by 2. So, therefore, this adds up to 0 and pi plus I3 is plus 1, S is 0, Y is 0, charge is 1. In pi 0, it is again 0, 0, 0, 0. Pi minus is minus 1, 0, 0, minus 1. Similarly, for the other mesons, K0 bar and K minus. So, we can see that this Gell-Mann Nishijima relation holds good for all the quarks as well as their bound states. In a similar fashion, we can also think about the Baryon octets, okay, and see that the same relation holds good there as well. Now, let us come to another aspect, masses of particles. In the SU3. We saw that, in fact, in the beginning when we discussed the isospin grouping, we said take pi plus, pi 0 and pi minus. We wanted to group them together because they are all having similar mass, about 140 MeV per c square. And similarly for K 0 and K plus, we said we could group them under the same isospin grouping because they have similar mass, about 500 MeV per c square. Similarly, proton and neutron also have mass about 940 MeV per c square. Both of them can be grouped together. So, the masses were the same more or less. But when we consider the octet of SU3, let us say the mesonic octet, we see that we wanted to group these pions along with K mesons and the antiparticles K 0 bar and K minus. They also have similarly about 500 MeV per c square mass. So, when we group these, all these particles in the octet did not have similar mass. You can see that here that the pions have mass for 140 MeV and kaons 500, something like 3 times plus, more than 3 times large, heavier. So, there is this kind of thing as per the symmetry goes can be accommodated. There is a difference in the masses can be accommodated by symmetry breaking, what is known as symmetry. So, the symmetry then we will say SU3 symmetry is not an exact symmetry, but it is broken down to SU3 is not exact symmetry, but it is broken down to SU2 isospin and U1Y. U1Y, again if you look at Y, we had defined Y, the hypercharge in the earlier slides. If you look at that, you will see that each of these isospin group will have a particular Y value. The SU3F is not an exact symmetry and it is broken, and the breaking is so that the groups with similar masses are grouped under SU2 or are symmetric under the SU2 grouping. Okay? And what can be but done is a kind of mass relation that can be worked out for SU2, SU3 multiplets. This is due to again Gell-Mann and independently by Okubo. So, this relation is known as Gell-Mann Okubo mass relation. Mass of any member with isospin I and hypercharge Y is equal to some K0, a constant, and a K1 times the hypercharge plus I times I plus 1 minus y square by 4 or y into y by 2 into y by 2. This is true for each super SU3 multiplet. So, for each SU3 multiplet K0, K1, okay, so there is another constant here, K0, K1 and K2 need to be found out, and once you fix that, then other members' masses can be, all the members' masses can be found out. For example, let us consider the Baryon octet, one of the Baryon octets. So, we have proton and neutron with I half, y equal to 1, because the Baryon number is 1. So, let me make it a proper table now. And there is this sigma 0 plus minus 1 belonging to I equal to 1, y equal to 0, cascade I equal to half, y equal to minus 1. Okay. And there is this lambda particle with I equal to 0, y equal to 0. Let me also write down the strangeness. Baryon number for all of this is equal to 1, we know, and strangeness is 0 for this, therefore, y is equal to b plus s equal to 1. Strangeness is minus 1 for sigma, therefore, y equal to b plus s is equal to 0, and minus 2 for cascade. So, it is equal to minus y equal to minus 1 for this, and lambda also has s equal to minus 1, b equal to 1, therefore, this is equal to 0, y equal to 0. So, now the mass relation will tell us that m half y1, that is one group, is equal to K0 plus y equal to 1. So, K1 plus K2 into I equal to half. So, I times I plus 1 is 3 by 4 minus, okay, let me write it in that fashion, 3 by 4 minus y is 1. So, y square is 1, y square by 4 is minus 1 by 4. Together in that bracket it is 2 by 4 or 1 by 2. And the other is I equal to 1 hypercharge 0 group, which is equal to K0 y equal to 0. So, K1 y equal to 0, but plus K2 into 3 by 4, sorry, this is not 3 by 4, isospin is equal to 1. So, I into I plus 1 is 2 and hypercharge y is equal to 0, it is 2, and you have m half and hypercharge minus 1, this is K0 minus K1, right, plus K2 3 by 4 minus 1 by 4. And there is an M00, the lambda, which has only the mass is equal to K0. So, you can see that if you know the mass experimentally of the lambda particle, then K0 is fixed. If you know the mass of sigma particles, then knowing K0, K2 is fixed, and the proton and neutron mass will fix K2. Then there is no more additional, no more free parameter, and therefore, the mass of sigma particle should agree with the relation given in here, where K0, K1 and K2 are determined from the masses of protons or neutrons, sigma and lambda. For example, we can write down the relation from here. is m half plus 1 plus m half minus 1 divided by 2, okay, you can work this out easily, is equal to 3 m 0 0 plus m 1 0 divided by 4. It is a simple algebra, you can just add this in this fashion and then you will get this. This mass relation is basically all due to the Gell-Mann Okubo relation, and then it is observed that this relation holds good in the case of this Baryon octet. Let us see that m of nucleon half minus 1 is m of nucleon plus m of cascade divided by 2 is equal to 3 times sigma mass plus mass of 3 times mass of the lambda particle plus mass of the sigma particle divided by 4. This is the relation predicted. Observed Mn is about 940 MeV per c square and M cascade is about 1315 MeV per c square. M lambda is about 1116 MeV per c square. M sigma is about 1193 MeV per c square. And that gives LHS of this relation is equal to 940 plus 1315 divided by 2. It is about 1128, right, just work that out, and RHS is equal to 3 times 1116 plus 1193 divided by 4 is about 1135. So, to a good accuracy, the relation holds good. How about the mesons? In the case of mesons, the mass relation is the square of the masses with same relation K0, where K0 will now may be different when you consider different group. So, K1 y, K2 I plus I into I plus 1 minus y square by 4. And that gives for the meson octets m k0 square plus m k0 bar square divided by 2 equal to 3 times m eta square plus m pi 0, say pion square divided by 4. And experimentally m k0 is and m k0 bar are about 500 MeV per c square, m eta is about 548, m pi 0 is about 135 MeV per c square. All are in MeV per c square, and you will see that LHS, work it out, is about 25, okay, and RHS is about 229784 with these numbers. These masses are not exact, okay, these are just approximate numbers. What is seen is that basically this mass relation holds better for the case of baryon multiplets compared to that of the meson multiplets. Okay. All right. So, this relation holds good for other multiplets like the decouplets and other octets, and octets when we consider other quarks also. Okay. So, these all such observations actually gave good faith in the quark model. But as I said earlier, we had to wait before actually confirming that there are particles called quarks, which are physical particles existing inside this one. For this, we had to do high energy deep inelastic scatterings, meaning you send probes, basically the electrons which are neutral as far as the strong interactions are concerned, send them at high energy inside these bound states like protons, and then the scattering of these particles of these ones now expected to scatter directly interact with the quarks inside this, if the quarks exist there, and bring out the information in the scattering distributions, etc., energy distributions, etc. So, this is what was observed later on, and then that gives us good faith in the quark model later stage. We will come to that a little later in a different discussion. Today we will close it here.